All right, on this video, we're going to talk about how to find the flux across an oriented surface. Flux should be a familiar term. We've talked about that before, but we'll talk. The difference here is when we're talking about a surface, that's different than when we're talking about flux across a curve in a plane. We'll talk about that with Green's theorem. So now they describe it as an oriented surface. Don't get too caught up on that. All that means is there's definitely two sides. Like you can talk about, here I have sort of maybe the upper half of a sphere where you could talk about being on the outside of the sphere or on the inside of the sphere. If you're familiar with a Mobius strip, that's an example of a surface that actually only has one side. And so we're only talking about flux over surfaces that have two sides. So anyhow, that's the difference. That's what they mean by oriented, but it's not usually a big deal. So our definition is the same. We want to measure how much of a field, we can think of it as liquid, gas, electromagnetic field that is crossing over a boundary, but this time the boundary is a surface. And so we want to do the dot product of F dotted with N, that would be the outward unit normal vector. And we want to integrate over the whole entire surface. On the last two videos, we talked about how to integrate, find the area of a surface, which we would call that d sigma. And we talked about two ways to find a formula for d sigma. So that's why there's really, in reality, two formulas for calculating the flux, all depending on how we want to talk about. Let's start with our unit normal vector. One way to find a normal vector to a surface, we've got an equation, is the gradient. That's the gradient vector. So we could have our formula being F dotted with it would be a unit vector, so we would go plus or minus the gradient because we want to make sure, usually when we do flux, we want to have flux passing outward away from the origin, let's say, over the magnitude of the gradient. So that's one way to calculate a normal vector to a surface. But as we've also seen, if you can parameterize a surface with two variables, you can also find a normal vector by doing the cross product. So you could do R sub u crossed with R sub v, I guess, again, plus or minus, because we want to make sure it's pointing one way or the other. And to make it a unit vector, we would divide by that magnitude. So either one of these formulas can go in for n, and depending on which formula you use, we've talked about a formula for d sigma that involves the gradient vector, and we've talked about a formula for d sigma that involves a parameterization of the surface in two variables. I did allude to this and just want to point out what's the difference here. We did talk about flux before, but before we were limited to a closed boundary, an area that was in a plane, usually the xy plane, and we have two ways we can calculate the flux across a boundary in a plane here. We could do it as a line integral, the line integral of F dotted with N ds, a little increment of arc length. And what we saw from Green's theorem is we could also do that as a double integral over the region of the divergence of F. Recall that was partial of M with respect to X plus partial of N with respect to Y, and we didn't talk about Z here because we were limited usually to the XY plane. So Green's theorem is the same. We're doing the same thing, but we're in the plane. But now we can talk about finding the flux across a surface that is not necessarily confined to the XY plane. Now, depending on which formula you use, back to our flux across a surface, you can get different, you can modify these formulas for flux. What will always happen, remember this is n, if I do F dot n, and I decide to use the gradient vector as my n, and remember our formula for d sigma, all of this is d sigma, we did that on the previous video. What will always happen, because you're doing f dot n times d sigma, the magnitude of the gradient vectors will cancel, and so we're just going to end up with the double integral of f dotted with plus or minus the gradient of f over the magnitude of the gradient of f dotted with p. That's one formula. Alternatively, if you use this formula for your unit normal vector, the parameterization formula, f dotted with n, here's d sigma when we use a parameterization, you can see that the magnitude of r sub u cross r sub v cancels out, and we really just end up with the dot product of f dotted with plus or minus ru crossed rv over the region. Every time you do it, so that this doesn't really look like the full definition of flux, but every time you do a flux calculation with this method or this method, you're going to get some stuff canceling out. So you could go straight to these formulas to calculate the flux. And so what I wanted to do is, for 3 examples here, show you how to calculate the flux of a field. Now we can have a 3-dimensional field. We can bring z in, which we couldn't do before, across a surface. And we're going to do it 2 ways, using both of those options for normal vectors. So here we're going to find the flux of the field across the surface, y squared z plus z squared equals 1, where z is greater than or equal to 0, which is a cylinder. It's the top half of a cylinder. So there's the top half of y squared plus z squared equals 1. And we stretch it out in the x direction from x equals 1 to x equals 0. So it kind of looks like almost like a covering, like a tent covering over this region here. Okay, so if we use this for our formula, then we're calculating the flux across this surface. So this would be our f function, and it's, remember, to find the gradient, a lot of times if there's anything, you move it over to one side, but as long as this is equal to a number, you're just going to take your 2 partial derivatives. So my gradient is going to be the partial of this with respect to x, which is 0, partial with respect to y, 2y, 2z. In the formula we're going to use, which, why don't we put it right here? The formula I just showed you, since we're using the gradient method, we're going to be doing the double integral over the region of f dotted with plus or minus the gradient of f divided by the magnitude of the gradient of f dotted with p over that area. Now my p vector, remember, that's the projection. It makes sense to project this surface on the xy plane. My p vector is a unit vector normal to that region. So in this case, as a lot of cases we've done before when we did surface area, my p is just going to be k. So the next thing I'd want to find, and the other thing too is when we calculate flux, okay, it didn't really indicate which direction. It said this field across this boundary. So I'm going to add here outward flux. Outward would sort of imply away from the origin, because you could talk about a field, how much of the field is crossing this way over the boundary, right? Now, and I say plus or minus, but hopefully you can see if I'm using positive x, y, and z values, this gradient vector is always going to generate positive y and z values. I'm going to be generating vectors that are going outward away. So I know that I just need to take the positive of that gradient. Now I need the gradient dotted with p, but my p is k. So it's going to be 0, 2y, 2z, dotted with 0, 0, 1. Gives me just 2z. And so if I have my gradient divided by my gradient dotted with p, let's just do that. Gradient over the magnitude of the gradient, sorry, dotted with P is going to be 0, 2y, 2z. Because my z is always positive, I don't really need to make it put absolute value or anything. It's going to be over 2z. So that's going to give me 0. If I divide those, I get y over z. 2z over 2z is just 1. Okay, so then let's bring it back to the integral. I'm going to be integrating over the region f, which was defined to be 0, yz, z squared, dotted with this 0, y over z 1 dA. That's on there once we get the dot product. Do the dot product, I get 0 yz times y over z. The z's are going to cancel, so I'm going to end up with 0, and then this is just going to be y squared, and then z squared times 1 is z squared. And notice on my surface, y squared plus z, that's the equation of my surface. So y squared plus z squared is equal to 1 in this case. So that's just going to be the double integral of 1 dA, which anytime we see that, all that just means is that is the area of R, of my region. And I can go back to my picture and see that that's just the area of this rectangle. Keep in mind that the circle intersects the y-axis at 1 and over here at -1. So this length right here is actually 2. It stretches from -1 to +1. This length went from 0 to 1. So this is just a rectangle, and the area of that rectangle is 2. Now to show you how this would look if we had used as our normal vector, plus if we did a parameterization instead, and we did plus or minus RU crossed RV over the magnitude of RU cross RV. Let's see what that would look like. So I'd have to parameterize my surface. And remember, my surface was y squared plus z squared equals 1. And I had some restrictions on what x could equal, right? X had to go from 0 to 1. So knowing that I have to somehow incorporate x into this, what I'm going to do is I'm going to let x be x, y be y, and if y was y, what would z equal in terms of y? Z would equal the square root of 1 minus y squared. I don't need plus or minus because it's the top half of that circle. So therefore, my parameterization in terms of just x and y is x, y, square root of 1 minus y squared. Now, the one thing I have to keep in mind here is which order. N says plus or minus, right? This. And so what I have to think about is which direction. So I'm going to redraw. Well, I can go back to my picture here. Back to my picture here. The cross product needs to be pointing outwards if I want outward flux. So if you think about this picture right here, R sub x, what is x? If you're at this point right here, you're moving in the x direction. That's going to kind of go this way, right? That's R sub x. R sub y is kind of going to be going this way in the y direction. So which way, when I do the cross product, will I get a vector pointing outwards? It's either R sub x crossed R sub y or R sub y crossed R sub x. That's why the right-hand rule is important. If you put your right hand around and pull R sub x into R sub y, you're going to get a vector pointing outward. So the correct way to do my cross product, if I was going to do that, would be R sub x cross R sub y. That's going to produce an outward unit normal. So I'll put note R sub x cross R sub y gives a normal vector pointing outward from the surface. But now the formula that we're going to use to calculate flux in this formula and integrate over the region we saw earlier, that if I'm using this formula, I don't need to actually divide by the magnitude because it's going to cancel out. It's just going to be F dotted with plus or minus the cross product. So now we know we should be doing F dotted with R sub X crossed with R sub Y, as opposed to R sub Y crossed with R sub X. What'll happen is if you do the wrong order, if you do the cross product the other way, you're going to get, in this case, probably a negative answer. And that's because you're calculating flux the wrong way. We know the answer should be positive 2. If you do it R sub Y crossed with R sub X, you're probably going to get negative 2. Okay, so now we need to figure out what R sub X crossed with R sub Y is. JK. Let's just take our partial derivative here. Partial of this with respect to X, 1, 0, 0. Partial of this with respect to Y will be 0, 1. Do a little chain rule in your head. Derivative of 1 minus y squared to the 1/2, 1/2 y, 1 minus y squared to the negative 1/2 times negative 2y. So the 2's are going to cancel out. I'm going to end up with negative y over the square root of 1 minus y squared. So I end up getting for my cross product 0, negative, oh no, but it's negative. You're supposed to be the negative already. Okay, so that's going to be the negative of negative. So that's going to actually be positive y over the square root of 1 minus y squared. Remember, the middle term gets a negative automatically. And then I'm going to get, for my z, I'm just going to get 1. Now, remember that 1 minus square root of 1 minus y squared is my z. That's z. So this is really y over z. So now if I set up my flux interval, f, well, it's f, I have it right there, f, which was way back when, 0, y, z, z squared, dotted with 0, this is y over z, 1. Zero, z's cancel, I end up with y squared, and then z squared times 1. Notice I get the same integral that we ended up with earlier. And so that's just the equivalent to the area of the region, because y squared plus z squared equals 1. So I get my answer of positive 2. So it works either way. And that's why I wanted to show you for 3 examples here, calculating the flux both ways, and you can decide which way makes the most sense. I find sometimes one method is easier than the other. Sometimes they're, but not either way is too bad. So it's nice to have options. Here's another one. Find the flux of y squared, yz x negative z squared across the parabolic cylinder, y equals x squared, where x goes from 0 to 1, z goes from 0 to 4, in the direction outwards towards the positive x-axis. So let's sketch this one. Remember, the way this works is you would sketch y equals x squared in the xy plane. That's a parabola. It's going to come out like this. But because x is only between 0 and 1, I don't need to go into the negative region. That's why I'm not drawing the other half. And then you just extend this in the z direction. Here it says from 0 to 4. So you're just going to get this parabolic sheet And so this is my surface right here. Okay, and so let's calculate this first using the RU. Okay, here I put using d sigma equals that, which is equivalent to n being plus or minus RU crossed RV over the magnitude of RU cross V RV. Same thing. So I want to parameterize this surface, and the natural parameterization here, I do need to bring z in there, so I'm going to let x be x, y is going to be x squared, and just have z be z. So I have r as a function of x and z is x squared, z. And oh, right. So we have to decide, okay, so this, okay, we want to do, to get our normal vector, we have to decide which is the correct order to do a cross product. So I can get a normal vector in this case, because how do we define which direction we want to calculate the flux? It says direction outwards towards the positive x-axis. So our field's coming in here, right? This is F. And we want to find how much of it is crossing outward this way towards the positive x-axis. So we want our n to be pointing this way, perpendicular to the surface, pointing outwards. They could have defined it to be crossing the other way towards the positive y-axis, but they defined it this way. Now, to figure out the correct order for our cross product, you want to think about the same thing. R sub x from this point would be sort of, imagine a vector on the surface that's kind of moving in the x direction. It's probably going to be moving, somewhat in this direction. That's R sub x, kind of towards the x-axis. R sub z is a little bit easier to imagine. That's going straight up. So take a second to think about which order, using your right-hand rule, would produce a vector coming outward this way. And hopefully you can see that n in this orientation, I want this to be R sub x crossed with R sub z. That's going to produce a vector that's pointing in the direction that I want, that they described. Okay, so then let's calculate that. So R sub x is 1, 2x, 0. R sub z, 0, 0, 1. R sub x crossed with R sub z. Block out the I and j, I'm going to get 2x minus 1, right? Because of the negative that you automatically put there, it's 1 minus 0. And then for my k component, 0 minus 0. So it's just 2x negative 1, 0. And in my formula for flux, integrate over the region, F dotted with, once again, I'm going to keep this paper handy. You are doing F dotted with n d sigma, but these two are going to cancel out. So it's just F dotted with, now we know it's R sub x crossed with R sub z. Over the area. So that's going to be F, way up at the top was y, z, x, negative z squared, dotted with 2x, negative 1, 0. So I get 2xyz minus x. And then for the z, I get 0. Oh, yeah. So this one has an interesting part to it, is that I want to be integrating over the region R. And let's go back to our picture here. The region R, if we take this back here, makes more sense to imagine this projected onto the xz plane. This is my region R, this little rectangle, which has x going from 0 to 1, z stretching from 0 to 4. So my region R, I can only integrate that with respect to x and z. But in my integral, I have y in there. So what we want to note is, I mean, I know this is the projection region, but on this surface, what's the equation of this surface? It's y equals x squared. Any point that's on the surface. So we get to replace this on the surface. Y is equal to x squared. So this turns into 2xy squared x. I just put 2x and then I was going to put in x squared times z minus x. So that would be 2x cubed z minus x. And now that I have x and z, I could just decide which way do I want to integrate this. It doesn't really matter. I could do dx dz. Remember from the picture, from the rectangle, x varied from 0 to 1 and z varied from 0 to 4. And this isn't too hard of an integral to do. So if you work that out, you should get an answer of 2. Wasn't that the answer I got on the previous problem? Okay, that's just a coincidence. The flux isn't always 2, but it came out that way for this particular field and this particular surface. Now let's see what this calculation looks like if I use the gradient method. Same function. So remember that this is on the surface. Y equals x squared. We have that same projection region. Actually, maybe need to redraw this. Let me just get a really quick drawing of this. Our plane is going like this. This was our surface, y equals x squared. And we're projecting this onto the xz plane. So this would be r, because remember with this formula, you need to decide on that p vector. And so in this case, your p vector, unit normal vector pointing outward perpendicular to this plane would be j. So then the gradient, now remember for an equation like this that doesn't have z in it, you can still think about f being the function x squared. If I move the y over, set that equal to 0, so I can still talk about the gradient vector being the three partial derivatives. Partial derivative with respect to x, with respect to y, with respect to z. I should mention this because we could have also defined f. I moved y over to the other side. I could move it over, could have moved the x squared over, and I could have gotten y minus x squared equal to 0. And I could have gotten for my gradient negative 2x, positive 1, 0. And that's why what I mean in the formula plus or minus, that's just the negative of this one, right? I could have gotten that as my gradient. So how do I know which one to use? You do have to think about it a little bit, and it all depends on how they define the direction they wanted us to calculate the flux. They said they wanted it outward. away towards the positive x-axis. They want our normal vector to be pointing this way. So if you think about it, a point on this curve, if you were to calculate the gradient by going -2 times the x value, that's going to take you in the opposite direction, right? The negative x direction. You're going to go this way with this part of my gradient vector. So I can tell that this is not the one I want. If I move this way, I'm going to be moving in a positive x direction, and I'm going to be kind of moving in a negative y direction, right? I'm going to be going backwards. And so it makes sense that my y would be negative. So this is the one I want to use for my gradient. And I hope what you're starting to notice is that when we do either of these methods, we have this decision to make about how we get our normal vector in the correct direction. You have to make sure you're taking the proper gradient, the plus or the minus. When we do the cross product technique, we have to make sure we're crossing in the right order to produce an outward normal in the direction that was specified. So either way, you don't really get any breaks. You have to think about it. Okay, so from here, this is my gradient. Remember my flux formula with this method is f dotted with plus or minus the gradient of f divided by the magnitude of the gradient of f dotted with p. My p is going to be j, so if I take 2x negative 1, 0, dot it with 0, 1, 0, I'm going to get 0, -1, 0. I'm just going to get -1, and it's the magnitude of that, right? So that's just going to be 1. So it really is just going to be f originally was given to be yz x negative z squared dotted with the gradient, which is 2x -1, 0, because this would be divided by 1. And if I work that out, I get 2xyz negative x, and then that's going to be 0 dA. And if you recall from what we just did, here it is. Yes, we can do the same thing. We're kind of in the same spot here. You could replace that y with x squared since we're on the surface. This is the same exact integral we came up with before. So this is going to be 2. One last one. Find the outward flux across the paraboloid z equals x squared plus y squared, cut on the top by z equals 1. So really just this part of the paraboloid, the outside, by this force field, vector field, 4x, 4y, 2. Outward, I think, would imply, there's stuff inside this little bowl kind of coming outward for this, right? So that would, I'd imagine for a point here, be pointing outward like this. That's what we want. Okay, once again, we'll try it both ways. This might be a good time to pause the video now that you've seen both ways. Try to calculate the flux, or at least set up the integral we'll start with this technique and using the other technique for your normal vector. Okay, so for this one, we have to parameterize. For a paraboloid, we've done this before. We're probably going to want to use r, right? Because z equals x squared plus y squared is really z equals r squared. So our parameterization is we're going to let x be r cosine theta, y equal r sine theta, and z itself is just equal to r squared. So r of r theta squared. And then we have this choice again to make. We have to decide what's the order we're going to do the cross product to produce a normal vector pointing outward. Another good chance, if you haven't done this already, pause the video and see if you can think about what you want to be thinking about is what direction does r sub r point in? Because we have to calculate that regardless, right? R sub r, and we have to do r sub theta, but then we're going to have to decide which way we want to do the cross product. I would think, let's think about r sub theta first. Remember that theta in the xy plane, we start along the x-axis, and a positive turn for theta is going this way. That would be counterclockwise. So if you were at this point and you were moving your theta, you were just rotating, you'd be going this way. So your r sub theta would be kind of pointing outward like this, a tangent to the curve, but kind of outward. That's r sub theta. Now, this is a little bit tricky, but if you think about which direction would you move in here for your radius, remember the radius is the distance this point is from the z-axis. That's what r is in polar coordinates. So to increase my r, notice you'd have to move higher up onto the paraboloid. If you want a bigger r, you want to move higher up. So r sub r is actually going to be pointing kind of tangent, but upwards on the parabola. That's r sub r. So to get a cross product that's going to be pointing outwards, the direction you'd want to cross it is r sub theta crossed with r sub r. If you pull r sub theta into r sub r with your right hand, your thumb's going to be pointing outward. So we're going to want, and I'll just go ahead and write it down so we don't forget, is going to be r sub theta crossed with r sub r. Okay, so let's get those derivatives. So we have negative r sine theta, r cosine theta, 2r. This is going to be, nope. Yeah. Okay, I did this backwards. That's r, I did them mixed up, didn't I? Let's start over. I did that one right. With respect to r, this is just going to be cosine theta. That's constant. This is just going to be sine theta. This one's going to be negative r sine theta, because I'm treating r as a constant, r cosine theta, and that's going to be 0. Okay, now we've decided on n. So r sub theta crossed with r sub r. It's going to give me the vector j 2r squared cosine theta minus 0 minus negative 2r squared sine theta minus 0. So that's going to be positive 2r squared sine theta. And then negative r sine squared theta minus r cosine squared theta. Let's write that. Minus r sine squared theta minus r cosine squared theta. Which can be reduced, right? This is the same thing as negative r times sine squared theta plus cosine squared theta, which is 1. So it's really just this, negative r. Okay, so then we can do our dot product. Oh, before we do that, on our surface, because my field was given in terms of x and y, it was 4x, 4y, negative 2. But remember, x was our cosine theta, y was our sine theta, so f is going to be 4r cosine theta, 4r sine theta, negative 2. Okay, now we're ready. So then flux F dotted with, in our case, R sub theta cross R sub R. Or R cosine theta, or R sine theta, -2, dotted with 2R squared cosine theta, 2R squared sine theta, -R. And that's going to give me 8R cubed cosine squared theta plus 8R cubed sine squared theta. That sounds good. I can simplify that. And then plus 2R. Oh, I got that backwards. Original function f was +2, so this should have been just +2 here. Let's fix that. So that's actually going to be -2R. Okay, obviously, hopefully, obviously this is going to be polar. It's going to work better in polar coordinates here, right? So this, if you factor out these 8R cubed, it's just going to leave you with cosine squared plus sine squared theta. So this is just going to be 8R cubed minus 2R times in polar r dr d theta. What are going to be the limits of my integral if I'm doing it in polar? The intersection of z equals 1 with z equals x squared plus y squared. My region of integration is just going to be a circle with a radius of 1, right? 1 equals x squared plus y squared. That's a circle with a radius of 1. And we know how to describe that. R is going to go from 0 to 1. Theta is going to go from 0 to 2 pi. You are going to want to distribute this before you integrate, but you should get an answer of, the last few I kept getting an answer of 2. This time I'm getting an answer of 2 pi. Okay, last bit here. Let's try the same problem. This one was a little more complicated using the gradient version of our normal vector. Probably need to draw. So remember our equation was z equals x squared plus y squared. If I want to use the gradient, then I have to think about the function. I have to make this, you can either do minus the x squared and y squared and set it equal to 0, or minus the z over. I'm going to minus the z over. So my gradient is 2x, 2y, -1. And like that, like the previous problem, how can I tell that that's the right way to do it? Or should I take this or the negative of it? But if I'm thinking what I want for n is something pointing outward, away from this, then it should be, there should be pointing in the positive x, positive y, and it looks like it's going to be coming down, right? Because the way the parabola is, normal to this is going to take you down a little bit because of how the parabola is. So that should make sense that that's negative. If you did the negative of it, you'd get a vector that's going the opposite way. So we've got the right gradient. Your projection region, like we did on the previous one, would be onto the xy plane. So your P is K. So then what else do I need? I need the magnitude. Well, let's find the gradient dotted with K. Hopefully you can see that if you dot this with 0, 0, 1, you're just going to get -1. So then I would have for my flux f dotted with the gradient of f over the magnitude of the gradient dotted with P. F was 4x, 4y, positive 2, dotted with 2x, 2y, negative 1, because I'm dividing by the magnitude of this, and the magnitude of that is just 1. So, and that leaves me with 8x squared plus 8y squared minus 2. Now we'd want to integrate this in polar because we've got this circle. So if I factor out the 8, x squared plus y squared is r squared minus 2. And if I was doing this in polar, there would be an r dr d theta. And my limits of integration would go from 0 to 1 and from 0 to 2 pi. Okay, and this is a good lesson in how you can catch mistakes here, right? Because if I distribute this r, I'm left with the integral from 0 to 2 pi, and that's going to be 8r cubed minus 2r dr d theta. Now we're doing the same problem that we just did with the other technique, the parameterization technique. So I should be getting the same answer, but notice I'm not. I got this part, but there was an extra r here. And so this is a good reminder, both for me and for you, that the mistake I made here was when you're doing the parameterization technique. You can go back and look at the video when we did parameterized surfaces. You don't, even though r and theta makes it look like we're doing polar coordinates, you can be using any two variables. My point is, when I did this integral this way, I did not need to add the extra r dr d theta. So back on the previous example, cancel that out, and I still think this will still give you 2 pi. But I did not need to have that extra r there. Yeah. And then I can see that these are exactly the same. So this integral should come out to be 2 pi. This should be the same. It's this one. Okay, so good lesson. All right, this has been a long video. We'll try to do a video on Stokes' theorem next, which is finding the circulation over a surface. Let me know if you have any questions, and thanks for watching.